The second flash talk is by Pilar López-Varo, and it's about the effect of ion distribution in perovskite solar cells.
Do you listen me? Yeah.
Okay.
Well, yeah, I'm going to talk about the effect of ion distribution in perovskite solar cells. This work has been done in the Department of Electronic and Technology of Computer in the University of Granada. Well, why I study the effect of ion distribution in perovskite solar cells? Because we can find some unusual experiment results, such as unusual temporal experimental results, the photocurrent, depending on the increasing time of previasing, we can observe a switching in the sense of the photocurrent. Even we can see low frequency dielectric responses under dark and under light conditions, and we can observe some hysteresis in current voltage curves. But the point is, what is the origin of these mechanisms? And well, in the literature we can find that they give us some explanation. They consider trapping and detrapping mechanism at the interface, capacitance mechanisms, or the movement of ions. In this work, we are going to focus in the effect of the presence and the migration of ions in the perovskite semiconductor. So to handle with this issue, we develop a simulator that simulates the perovskite solar cells as a solar cells with ions. We consider the Poisson equation, the diffusion equation for electron and holes, and continuity equation for electron and holes. So this set of equations, the perovskite solar cells, the performance of the perovskites, is very well defined. Now, in order to consider the presence and the migration of ions, we can consider two approaches. The first one is considered that the ions move by diffusion mechanisms. So we consider the diffusion equation for cation and anions and the continuity equation. Or the second way, we consider a dipolar distribution of ion. We fix the dipolar concentration of cation and anions at the interfaces of the perovskite semiconductor. Here I'm going to show you some of our results. First, here I show you the migration, the result that we obtained when we simulate the migration of one or both type of ions in the perovskite solar cells, because this is an open question. What are the type of ions which move in the perovskite semiconductor? And here we observe that is completely different the result that we get when we consider that the cations move and the anions are constant and doesn't move in the perovskite semiconductor. In this case, we simulate how the anions move, and as Juan says, there is an inversion of the energy diagram. In this case, this solar cell works as a p-type solar cells, and in this case as n-type solar cells, and in this case we simulate that the anions and cations move in the perovskite semiconductor. So as a result, we observe that there is a different distribution of mobile ions appear in the case under study, and in general they act as if the doping of the semiconductor is modified. Then here I show you a comparison between consider the deep diffusion or the dipolar distribution of ions. This is for the case of the deep diffusion equations, and this is for the case of the bipolar distribution of ions. You can observe that there is a difference between both cases. And in this case, there is a strong screening of the electric field at the bulk. And here in this case, the electric field is now zero in all the devices. So as we can see in the literature, the hysteresis is explained by the slow movement of ions in the perovskite. And with this picture or with this approach, the explanation of this current voltage curve will be completely different. Then we study again the comparison between the diffusion and the dipolar distribution of ion, in this case for open circuit voltage. And we observe that in the case of a dipolar distribution, we obtain a non-zero electric field at the bulk, a difference to the considering the diffusion mechanisms. This is, in this case, we study the interface, because in the literature it is observed that there is, and as Juan says, there is a strong accumulation of holes at the interface, and with this simulator we can evaluate how is the effect of the ion distribution close to the interface, and we can evaluate how it affects to the in the hole concentration close to the interfaces. And well, I would like to suggest to read this paper and enjoy reading it. And well, this work has been done obviously in collaboration with Professor Juan Vizquer, Agustin and Sandeep, and Professor Antaf. And thank you very much for your attention.